Oh, hello. I didn't see you there. I'm your host, Daniel Pinto, and together with Ankarchun Riesman and Austin Reich, we are the HAGGIS Gang. Over the past couple of weeks, we have analyzed the Clyde Arc in Glasgow, Scotland, for our basic structural analysis class. Join me on this journey. Moving on to the selection process and a couple general facts. Firstly, the Clyde Arc is located in Glasgow, Scotland, and is a three-span discontinuous structure connecting Finnieston to Kinning Park. It is important to note that the structure is located less than half a mile away from the M8, which is Scotland's busiest highway, leading to an ADT of over 6,000. The Clyde Arc was built as a representation of the increased effort to redevelop some of the southern parts of the city, providing an iconic gateway to the northern parts. Couple this with the fact that the construction of this structure would create over 3,000 jobs, and it is no surprise why the Glasgow City Council was on board with this project. Then, just to provide a little brief timeline, in 2000 the project was advertised, 2003 planning permissions were granted, 2005 construction began, and in 2006 the Clyde Arc was completed. Moving on to the load path, the Clyde Arc is a steel bowstring asymmetrical tied bridge. And so what that means for us is that the load path is as follows. First, the load starts on the deck. Then it's transferred through the steel girder system, then transferred up through the cables, into the arc, down to the piers, and eventually down to the foundation. Now, in order for us to complete our calculations, we had to make a couple assumptions in order to idealize this situation. Doing that, we focused on the main deck of the bridge, which has a length of 96 meters and a width of 21.3 meters, which we divided into 4 notional lanes of 5.325 meters. And so, per the BS 5400 standards, 3701 and 2101, we were able to calculate our live loading and dead loading. Additionally, we assumed an area load, making our calculation a bit easier. And as you can see, we divided the deck area into 14 parallelograms of equal area applied at each cable end. Additionally, we assumed equal distance on the arch between each cable on its respective side. For example, when you're looking at it from the north, you can see each of the 7 cables are spaced evenly. Our last assumption was that moment was 0 at the top of the arch for equation's sake. Wrapping up the idealization a bit, according to the BS 5400 standards, for the determination of local effects of an area load, a load factor, gamma F1, is applied at a factor of 1.6 for live loads and 1.2 to dead loads. Additionally, we applied the additional load factor, gamma F3, which is used to obtain design load effects for extreme and normal loading scenarios. 1.15 we used for the normal and 1.4 for the extreme. The way we factored these in was by multiplying them by our total loading scenario. Because the load path of the bridge starts in the deck and then goes to the cables, the tension force in the cables needs to be calculated first. The Clyde Arc has 14 cables that attach the deck to the arc. Each cable has a pair in which they're attached to the deck at the same angle. Because of this, we did one calculation for each pair of cables, calculating tension and girder force. We used the sum of the forces in the y direction to calculate the tensile force and the sum of forces in the x direction to calculate the girder forces. 2 major piers at the bottom of the arc are pinned and thus have x and y reactions. There is a distributed load on the top of the arch, which is the weight of the arch itself. We turn this value into a point load for our calculations. The red arrows pointing down from the arch are the tensile forces in the cables, which are all the same. As previously mentioned, there is a hinge at the center of the arc to represent 0 moment. We then made a cut at the hinge and took the sum of the moments at that point, which gave us the x reaction value for the major pier. From there, it was statics. The deflections we expected to see occurred downwards along the deck as well as diagonally between the major piers. Because of this 3D deflection, we cannot calculate our deflection in 2 dimensions as a beam. Thus, we had to use STAD Pro for our deflection calculations. In STAD Pro, we first modeled the girder system underneath the deck. According to an Institution of Civil Engineers report, varying girder depths were given, so we decided on a uniform depth of 1,700 millimeters. Additionally, no dimensions were given for the I-beams, so we estimated our data on the figures given and on ratios. Additionally, a cable is present in the bridge, taking the X-reaction forces from the major piers. This is shown running diagonally across the deck between the 2 major piers. Originally, we wanted to run the analysis using only the major piers. However, the program would not do this, so we added in the minor piers, assuming the presence of only Y reactions. The load cases were developed by taking the tributary area of the deck resting on each beam, then multiplying it by the area dead and live loads. The resultant loads are shown in the table. These loads were then applied to each beam in the system. Our analysis shows that the max deflection occurs at the center span. In the normal case, this was 3.4 centimeters, and in the extreme case, this was 4.8 centimeters downwards.
That's about it for me. It's been a pleasure leading you on this journey. If you have any questions, comments, concerns, similar projects to ours, please comment down below. We'd love to interact with you. We're some passionate engineers. Visit Glasgow, have some haggis. Have a good one.